Billions of years ago, something incredible happened. Our universe was born from nothing in less than a second. But here's the part that will blow your mind. Scientists have discovered that our entire universe might be just a bubble floating in something much, much bigger. Imagine a bathtub full of soap bubbles, where each bubble is a different universe with its own laws of physics. Some of these bubble universes might have different gravity, time that runs backwards, or even more dimensions than we can imagine. And the most shocking thing of all, there could be infinite bubbles out there, each with its own version of reality. This means everything we know, stars, planets, even you, exists only inside a tiny bubble floating in an endless ocean of other worlds. How does this change everything we thought about our place in the cosmos? Subscribe to the channel, leave your like and comment from what part of the world you're watching, because now I'm going to tell you everything. Could the part of reality we can measure be only a small area inside a much larger space? This is the key question behind the bubble universe idea. The idea says our observable region might be the inside of one bubble. Space beyond our view could hold other bubbles. Each bubble can follow different basic rules. Those rules decide how particles behave and how forces act. They decide how space itself is shaped. I will use very simple words. I will explain the main ideas and the main terms. I will also explain why the idea matters and how scientists try to test it. What a bubble means here. A bubble is a region of space that has one set of physical rules. Inside that region, the forces and the particles follow the same laws. Outside that region, in another bubble, the laws can be different. The boundary between two bubbles separates those different rules. The boundary can carry energy and can push on nearby space. The word bubble does not mean anything soft or round in the usual sense. It is a short way to say a region with one set of rules. I will use that word to keep the idea clear. What a state means. A state is a choice for how the fields that fill space are set. Fields are basic things that exist everywhere. Fields can have different values in different places. When a field takes a particular value, it sets the properties of particles and forces. That set of values is a state. A bubble forms when a region of space settles into one state and stays there. What a physical rule means. A physical rule is any law that tells matter and energy what to do. Physical rules include the strength of gravity. They include which particles exist and how heavy they are. They include the charges of particles and how forces act at a distance. They include the shape and number of spatial directions. A change in a state can change these rules. Where the idea comes from, the bubble idea grows from a simple model of very fast early expansion called inflation. Inflation means space grew very fast for a short time early on. During inflation, tiny random differences can be stretched to large size. Those tiny differences come from quantum physics. Quantum effects make very small random changes in fields. Inflation takes those small changes and makes them large. When different places settle into different states, each place becomes a bubble. Each bubble can then carry its own physical rules. The rules inside one bubble can be slightly different or very different from the rules in another bubble. The range of possible rules depends on the theory that describes the fields. Some theories allow only a small set of possibilities. Other theories allow many possibilities. Why the idea matters. If the bubble idea is true, what we measure in our region is not the full story. The constants and laws that we call fundamental might be local features of our bubble. That means they could be different in other regions. The fact that our bubble allows atoms, stars, and observers then invites new questions. Why does our bubble have the right rules for complexity? Are our rules common among bubbles, or are they rare? These questions change how we think about fine-tuning and the origin of laws. Basic examples of different rules. Rules can change in many ways. Gravity might be stronger or weaker, particle masses might be different, electric charges might have other values. Some bubbles might have extra spatial directions that are real, but that particles cannot move in the same way we move. Some bubbles might not have any particles like the ones we know. Some bubbles might not allow stable atoms. The differences can be small. A small change in a mass or in a charge can alter chemistry and the formation of stars. The differences can be large. A large change can prevent stars from forming at all. Some bubbles may be simple and empty. Some may allow complex structures. What we can see from inside one bubble, we live inside one bubble. The part of space we can see is the observable universe. It is the region where light and other signals had time to reach us since the beginning. Other bubbles could be beyond that region. If they lie beyond our cosmic horizon, no signal from them can reach us. Those bubbles would remain forever out of direct reach. Other bubbles might have met ours. If two bubbles grow close enough, they can collide. A collision can change the local shape of space and the values of fields. That change can send information into our region. It can leave marks that we can try to find. How collisions can leave marks. A collision can push on the field values and on space itself. The push can change the density of matter and radiation in a part of our bubble. It can change the pattern of temperature in the ancient light that fills the sky. It can send out ripples in space called gravitational waves. It can create long-lived structures or defects in space. It can inject energy that slightly changes the spectrum of the background light. The marks of a collision are often small. They can be weak enough to be hard to see. They can be localized to one patch of the sky. They can appear as circular or ring-like features in maps of ancient light. They can make small changes in the orientation of light. They can produce a pattern in how galaxies cluster on the largest scales. Signals that can be searched for scientists use several ways to search for signs of other bubbles or of collisions. One major route is the cosmic microwave background. That is the ancient light left over from a time when the universe became transparent. It fills the sky. It carries tiny variations in temperature and in the orientation of the light, which is called polarization. A collision that happened early enough could leave a pattern in that light. Another route is gravitational waves. Collisions and other bubble dynamics can send out ripples in space-time. Instruments on Earth can detect some of these ripples when they are in the right frequency band. Instruments in space can detect other frequencies. If a collision created the right kind of wave, we might measure it. A third route is the large-scale distribution of matter. Surveys of galaxies map where galaxies sit across the sky. A past collision can shift how matter clumps in a region. Careful maps can reveal patterns that are hard to make by ordinary growth. A fourth route is the precise measurement of the background spectrum. The ancient light has a nearly perfect blackbody shape. Tiny injections of energy can slightly distort that shape. Sensitive instruments can search for those distortions. A fifth route is searches for relics. Collisions could produce defects or unusual fields that survive to late times. Particle experiments or astrophysical observations could find their effects. Why testing is hard? All searches face big difficulties. First, the signals can be extremely faint. Disturbances from collisions may be much smaller than the typical variations already present. Second, foreground emission from our galaxy and from other astrophysical sources can hide or mimic the signals. Third, instruments have noise and limited resolution. Fourth, some possible signals can be created by ordinary physics in our bubble. Scientists must rule out these ordinary sources before claiming a detection. There is also a fundamental limit. The universe gives only one large-scale sample. This fact is called cosmic variance. It means that for the largest patches of sky, we have only one example. That limits how precisely we can separate a rare, real signal from a random fluctuation. Theory also adds limits. Different models of inflation and fields predict different types of bubbles and different collision signatures. The range of predictions can be wide. To know what to search for, scientists need many simulations. Building accurate simulations is hard and costly. How scientists try to meet the challenges. Scientists take several steps to meet these challenges. They make full-sky maps of the ancient light and its polarization. They remove foreground emission from our galaxy as carefully as possible. They measure instruments well so they can model the noise. They create many simulated skies that follow known physics. They add simulated collision signals to those skies and ask whether their analysis would find them. They also cross-check using different data sets. A pattern in the ancient light that also links to a pattern in the distribution of galaxies would be stronger than a pattern in the ancient light alone. A gravitational wave signal that matches a predicted frequency and a predicted shape can strengthen a claim made from other data. Scientists use statistics to measure how likely a given pattern is to arise by chance. They use careful tests to reject ordinary explanations. They demand strong evidence before declaring a discovery. This careful approach is needed because of the many ways a false claim can appear. How inflation makes the idea natural. Inflation offers a simple path from tiny quantum effects to many large regions. During inflation, space grows very fast. Tiny random differences in the fields that fill space can become large regions as expansion stretches them. When the field in a region settles into a state, that region becomes a bubble. Different places can settle into different states. Thus, inflation gives a natural mechanism to make many bubbles with different rules. The details matter. The shape of the field potential and the laws that govern quantum effects set how often different states occur. Simple models show how many bubbles can form. More complex models allow a larger variety of states. The range of possible states sets the range of possible bubbles. Why our bubble seems special? Our bubble has rules that allow long-lived atoms, stars, and galaxies. These structures made planets and the chemical elements needed for life. This fact raises a question. Why does our bubble have these life-permitting rules among all possible bubbles? The question does not yet have a single answer. Some scientists think the answer involves selection. Observers will only find themselves in bubbles that allow observers. Others search for deeper physical reasons that make our rules more likely. This is an active area of thought and of research. The bubble idea changes how scientists frame the question. The focus shifts from only finding a single set of laws to also asking how those laws might vary across different regions. What a clear detection would change. A clear and convincing detection of another bubble or of a collision would change physics. It would force new rules that describe how bubbles form and how the internal laws are chosen. It would connect cosmology and particle physics in new ways. The idea of fine-tuning would be seen under a new light. Values that now seem special could be explained as features that only certain bubbles have. A detection would open a new field of study. Scientists would try to map the diversity of bubbles. They would seek to measure the range of physical rules that exist in other regions. The search would expand into many experiments. New detectors and new surveys would be designed to measure signals with greater sensitivity. But a clear detection is hard to get. The marks can be small. Many mundane processes can produce similar marks. Careful confirmation is essential. A clear start and the work ahead. The bubble universe idea gives a different way to think about the origin of our observable region. It says we may live in one of many regions that can have their own laws. The idea is grounded in simple models of early rapid expansion and in the known fact that quantum effects can produce small random differences on small scales. To make progress, scientists use many kinds of data. They map the ancient light across the full sky. They measure its polarization. They build instruments to search for gravitational waves across different frequencies. They map galaxies and measure their clustering on the largest scales. They build precise spectrometers to check the shape of the background light. They run large computer simulations that show how bubbles form and how collisions look in the signals. The work is hard. The tests need careful modeling and deep data sets. The signals can be rare and weak, yet the payoff would be large. Even one clear sign would change how we understand the laws of nature. Understanding the next step. To see how separate bubbles can form, we must look closely at inflation and at how tiny quantum differences are stretched into large regions. That process explains how fields can settle into different states in different places and how bubbles with distinct rules can appear. The next topic explains how inflation works in simple terms and how it makes separate bubbles across space. How can a very small random change grow into a whole region that ends with its own state? Inflation is a period when space grew very fast for a short time. A field filled space and gave it energy. That energy made space expand faster than normal. The expansion stretched distances very quickly. The field controlled how long this rapid expansion continued. A field is a quantity that exists everywhere. The field has a value at each point in space. The energy of the field depends on its value. The relation between field value and energy is called the potential. The potential tells the field how easy or hard it is to move from one value to another. If the field moves slowly where the potential changes little, the energy stays almost constant for a while. That constant energy pushes space to expand rapidly. This rapid expansion is inflation. It can last a short time. It can end when the field moves to a value with much lower energy. Quantum physics says fields cannot have a perfectly fixed value at very small scales. The field has tiny random shifts. These shifts are called quantum fluctuations. Quantum fluctuations are always present at very small scales. When space expands very fast, it stretches these tiny random shifts to larger sizes. A small shift that would normally live only at a tiny scale can grow to cover a much larger patch. At a certain point, the stretched shift becomes larger than the distance that light could cross during the same time. That distance is called the horizon. When a fluctuation grows larger than the horizon, it stops being able to change by signals that come from outside. In that sense, the local field value becomes frozen for a long time. These frozen field values act as local differences. Different regions that stop changing can carry different values of the field. Those regions can then evolve on their own. Each region with a distinct frozen value can develop differently once inflation ends there. There are two main ways separate regions with different states can appear during inflation. One way is through continuous variation of the field value. The field moves slowly down the potential. Quantum fluctuations push the field up and down by small amounts at many places. Where the field gets pushed slightly farther forward, inflation ends a little sooner. Where the field is pushed back, inflation lasts a bit longer. This process makes a patchwork of regions that end inflation at different times and with different local field values. The other way is through a sudden jump. In some potentials, the field can sit in a high-energy state that is not perfectly stable. That state can last for a while. It is called a metastable state. The field can then make a quantum jump across a barrier to a different, lower energy state. That jump creates a small patch of the lower energy state inside the surrounding high energy region. That small patch can grow. When it grows, it becomes a bubble. The jump across a barrier is called quantum tunneling. Tunneling is a purely quantum process. It allows the field to move to a state that it could not reach by ordinary slow change because of the energy barrier. The chance that a tunneling event happens depends on the height and width of the barrier and on the field values. Scientists can compute a rate for such tunneling events. They call that rate the nucleation rate. A nucleation event starts as a small patch of the new state. The boundary of that patch is the wall of the bubble. The wall is a region where the field changes from the inside value to the outside value. The wall carries energy. The wall moves outward into the surrounding space. It moves very fast. The expansion of space also affects how the wall moves. When a bubble grows, the inside region can follow different paths. In one common case, inflation ends inside the bubble. The energy that drove inflation converts into particles and heat. That conversion begins a hot expanding phase inside the bubble. That hot phase can then lead to the ordinary expansion and cooling that allows matter to form atoms and stars. In another case, inflation may continue inside the bubble for some time. Then the interior will inflate further before reheating. The local history inside each bubble can differ depending on the field value inside and on the shape of the potential. When bubbles form and grow, many can appear in the inflating space. Whether many bubbles grow and meet each other depends on two competing effects. One effect is the expansion of the inflating space itself. The other effect is the rate at which bubbles nucleate. If bubbles nucleate frequently enough, they can fill much of the space. If bubbles nucleate rarely and the inflating region expands very fast, the inflating region can grow in volume faster than bubbles can occupy it. In that case, pockets of inflating space persist and keep producing new bubbles. This process can continue without end on the largest scales. Scientists call this behavior eternal inflation. Eternal inflation changes the global picture. Some places stop inflating and become bubbles. Other places keep inflating and expand faster. Over time, the volume of inflating space can grow without limit even while bubbles form inside it. Each bubble becomes a local non-inflating region inside a still inflating background. The details of the potential control which of these behaviors happen. If the potential has many low-energy states separated by barriers, then tunneling can produce bubbles with many different internal values. If the barriers are low or narrow, tunneling happens more often. If the barriers are high or wide, tunneling is rare. If the potential has a broad, slow region rather than distinct separated minima, then the field will move slowly and quantum fluctuations will create a range of values across space without sharp bubble walls. The kind of bubble that forms also depends on the energy difference between the inside and the outside. If the bubble interior has much lower energy than the outside, the wall will carry a lot of energy and the dynamics can be violent. If the energy difference is small, the wall will be less energetic. The wall energy affects how the wall moves and what it leaves behind. When bubbles form in an inflating background, the wall motion and the expansion of space set the geometry inside the bubble. In many tunneling cases, the geometry inside a newly formed bubble has a particular curvature. That curvature evolves as the interior expands and as matter and radiation fill the region. The final large-scale geometry seen from inside the bubble depends on the details of the early expansion and on the field dynamics after the bubble forms. Bubbles can collide. When two expanding bubbles meet, their walls crash into each other. The collision changes the fields near the meeting region. The collision can cause the field in that area to shift to a different value or to oscillate. The energy released by the collision can generate waves in the surrounding space and radiation. The outcome of a collision depends on when it happens, on the wall energies, and on the field values inside each bubble. Collisions that happen early, before the hot phase inside a bubble begins, can leave marks in the radiation that later fills that bubble. Collisions that happen later, after matter and radiation exist, can change how matter clumps in the affected region. Collisions can also produce waves in the fabric of space. These waves are gravitational waves. The strength and frequency of these waves depend on the energy scales involved. The process that turns the field energy into particles and radiation is called reheating. Reheating happens when the field that drove inflation loses its uniform energy and transfers it to ordinary fields that make particles. The details of reheating affect the temperatures and particle content inside a bubble. Those temperatures and particle mixes set the later path toward forming atoms, stars, and galaxies. Quantum fluctuations have another role. They are random. That means the values taken by the field in different regions are not fixed by one rule. Instead, inflation plus quantum fluctuations produce a probability distribution over possible local values. Scientists can compute that distribution in a model. The distribution tells how likely it is that a given region will end up near one value or another. Those probabilities feed into predictions for how many bubbles of each type might appear. Even though the process is random, some outcomes are more likely than others. The relative likelihoods depend on the potential and on the dynamics during inflation. In models where the potential has many minima, the distribution of minima reached after inflation can be complex. The number of possible minima can be large. Each minimum corresponds to a distinct possible state inside a bubble. When a bubble forms and its interior evolves, the local conditions inside that bubble can set the strengths of interactions and the masses of particles. Those conditions follow from the field values that settle inside the bubble. Because the potential can allow many different settled values, bubbles can end up with different internal rules. In some models, the set of possible rules is small. In other models, the set is very large. A large set allows many kinds of bubbles to appear across the inflating background. The motion of bubble walls matters for observations. A wall that moves through a region can change the density of matter or radiation there. It can also change the field values in its wake. Walls can generate shocks that heat the medium they pass through. Walls can leave topological defects or unusual field patterns that survive to late times. These relics can provide evidence that bubbles met and that the field underwent a change. Scientists try to model these processes with computer simulations. A simulation represents space on a grid and follows the field values in each cell. The code evolves the field using rules that come from the potential and from the expansion of space. The simulation can track bubble nucleation events, wall motion, collisions, and reheating. Running many simulations allows scientists to build a catalog of possible outcomes. That catalog helps to translate a theory of fields into predictions that observers can test. The rate at which bubbles appear and the typical size they reach before colliding depend on the nucleation rate and on the expansion rate. If bubbles appear very frequently, they can collide soon after forming. If nucleation is slow, bubbles can grow very large before meeting another bubble. The probability that our observable region shows a collision imprint depends on these rates and on when our bubble formed. Another key point is timing. If a collision happened before the radiation that today forms the cosmic microwave background stopped scattering, then the collision can leave a signature in that ancient light. If the collision happened later, it might leave a pattern in how galaxies form. If it happened very early, it might alter the global geometry in a way that is hard to detect inside the bubble. The energy scales involved also matter. If the energy difference between states is high, the Wall energy and the waves produced by collisions can be strong. Strong signals are easier to detect. If the energy scale is low, the signals will be weak and more difficult to separate from other sources. All of these factors make predictions model dependent. Different simple potentials give different kinds of bubbles and different collision signatures. That is why scientists study many models and run many simulations. The goal is to find robust features that show up across models and that can be searched for in data. One clear result from the basic theory is that inflation magnifies small quantum differences into large, causally separate regions. Those regions can then settle into distinct states. A state is simply a set of field values that remains stable over long periods. Once a region settles into a state, that state controls what happens inside that region. It sets the energy available, the types of particles that appear, and how forces act at low energies. The process of bubble formation has a few intuitive steps in simple language. A tiny random change appears in the field. Inflation stretches that change to large size. The stretched region becomes effectively isolated from its surroundings. If the change crosses a threshold set by the potential, a bubble of a new state can form. The bubble wall expands and the inside relaxes to its new values. Energy converts to particles and heat. The bubble then follows its own local history. Because the underlying process is quantum and random, predictions are probabilistic. Scientists can say which outcomes are more or less likely. They can compute the expected number and size distribution of bubbles for a given potential. They can also estimate how often collisions should be strong enough to leave observable imprints inside a bubble. The overall picture also raises a general idea. Inflation can create many separate regions that do not share the same local field values. Each such region can settle into its own state. The details of the potential and of the quantum dynamics determine how many different states are accessible and how often each state appears. When a region settles into a particular state, that state sets the basic rules that govern matter and forces inside that region. The next step is to see how changing the state changes those rules. Understanding that link explains how two bubbles can end up with different laws of physics and how those differences affect the formation of atoms, stars, and galaxies. When a region settles into a state, that state sets the numbers that control what happens inside. Those numbers decide how strongly forces act. They decide how heavy particles are. They decide which kinds of particles exist and how space itself behaves. This link from a state to the numbers of physics is the key idea. It explains how two bubbles can have different laws of nature. A state is a set of values that fields take across a region. A field is something that exists everywhere. The value of a field gives a number. That number appears in the equations that govern particles and forces. When the field value is fixed across a region, the numbers in those equations stay fixed there. Those fixed numbers are what we call physical constants. A change in the field value makes a change in those constants. One clear example comes from a field that gives mass to particles. Some particles gain mass because they interact with a field that has a non-zero value across space. When the field value changes, the mass of those particles changes. A simple statement is this: if the field value is small for a particle, that particle is light. If the field value is large for that particle is heavy. The mass affects how the particle behaves at low energies. Heavy particles may not appear in the ordinary world. Light particles can shape chemistry and radiation. Forces also depend on numbers set by fields. Each force has a coupling constant. A coupling constant is a number that sets the strength of the force. The electric force has a coupling constant that sets how strongly charged particles pull on one another. The strong force has a number that sets how tightly protons and neutrons bind inside nuclei. The weak force has a number that sets certain particle decays. If the coupling numbers change, the behavior of particles changes. Reactions that happen easily in one state may become rare or impossible in another state. Another key number is the strength of gravity. Gravity is described by a number that tells how strongly matter bends space and pulls on other matter. In practical terms, that number helps decide the sizes and lifetimes of stars. It also helps decide how matter can clump into galaxies. When the gravity number is different, the large-scale evolution of matter is different. Some fields set the number that controls the overall expansion of space at late times. That number is often called the vacuum energy or the cosmological constant. A large positive vacuum energy makes space expand fast. A small vacuum energy makes expansion slow. When the vacuum energy is too large, matter and radiation cannot clump in the usual way. When it is very small or slightly negative, the expansion pattern changes in other ways. The vacuum energy is itself a number set by the field values inside the state. Fields can also determine the pattern of symmetries in the low-energy world. A symmetry is a rule that leaves some features unchanged under a transformation. When a field settles in a state, it can break some symmetries. Breaking a symmetry can create differences among particles. It can give mass to some particles while leaving others light. It can split a single force into separate forces. Different states can break different sets of symmetries. That produces different sets of particles and different force relationships. Some theories include fields that control extra spatial directions. These extra directions are small and curved in some models. The shape and size of those extra directions are set by field values called moduli. When a modulus field takes one value, the extra directions can be small and produce one kind of low-energy physics. When it takes a different value, the extra directions can be different and produce another kind of physics. The pattern of particles and force strengths can change when the extra dimensions settle in a different shape. The list of possible states depends on the underlying theory. In some simple theories, there are only a few stable states. In other theories, there are many stable or metastable states. When the number of states is very large, the set of possible low-energy laws is very large. In those cases, bubbles in different places can end up with very different low-energy rules. The variety of outcomes can be small in some models and huge in others. A practical way to think about the link between a state and the low-energy laws is this. The state fixes a set of numbers. Those numbers feed into the equations that govern particles and forces. The solutions of those equations determine whether atoms can form, how nuclei bind, and how light interacts with matter. Those solutions then determine whether complex structures can form and evolve. Now we can consider concrete effects. One important ratio is the mass of the electron compared to the mass of the proton. That ratio controls atomic sizes and the energy levels inside atoms. If the ratio changes, the shapes and energies of atomic orbitals change. Chemical reaction rates and bond strengths change. Molecules that form under one set of numbers may not form under another. The nature of chemistry depends sensitively on this ratio. Another key quantity is the strength of the electromagnetic force. That strength sets how tightly electrons bind to nuclei. It also affects how radiation interacts with matter. if the electromagnetic number changes, stars cool and heat differently. The formation of molecules, dust, and other building blocks for planets depends on this number. The balance between electromagnetic and nuclear forces also affects the stability of nuclei. Nuclear physics depends on the strong force and on the masses of quarks. The strong force binds protons and neutrons into nuclei. When the strong force number changes, the binding energy of nuclei changes. If nuclei are bound more tightly, fusion reactions in stars may proceed with different thresholds. If nuclei are bound less tightly, some forms of heavy nuclei may not exist. The masses of the lightest quarks also affect the mass difference between protons and neutrons. That mass difference sets whether hydrogen is stable and whether nuclei have the right mix of protons and neutrons to form heavy elements. Particle decays and lifetimes depend on coupling numbers and on available energy. If a state gives new decay channels or faster decay rates, important particles can be short-lived. For example, if the proton were unstable on short timescales, ordinary atoms would not survive long. The stability of protons in our region depends on the symmetries and couplings set by the state. In some states, protons may be effectively stable. In others, they may decay on short times. The number of massless or light particles matters too. Light particles contribute to the radiation content of the early universe. Radiation content controls the expansion rate in the early phases. That expansion rate affects the growth of small variations that later become stars and galaxies. Extra light species change the timing of key events, such as the formation of the first atoms. A state that produces many light particles can change the whole history inside the bubble. The pattern of particle charges is also important. Charges are numbers that determine how particles couple to forces. If the charge assignments are different, atoms can have different sets of allowed bound states. The chemistry that can develop will differ. Strong constraints exist for charge quantization that allow neutral atoms to form at all. Changing the pattern of charges can prevent neutral atoms from forming. Some states produce new types of particles that do not exist in our region. Those new particles can be heavy and short-lived, or they can be light and stable. A new stable particle can contribute to the matter content. That change alters how structures form and how radiation interacts with matter. A new heavy particle that decays late can inject energy at late times and disturb processes such as the formation of the cosmic microwave background. The geometry of space itself can differ. The curvature and topology at large scales depend on the early dynamics inside the bubble and on the vacuum energy set by the state. Some states lead to space that is effectively flat on large scales. Other states can give slight curvature. Curvature changes the relationship between distances and volumes. It shifts the way matter clumps over the largest scales. Observers inside the bubble will measure these geometric features and infer the underlying numbers. Stability of the state is also a matter to consider. Some states are stable for extremely long times. Others are metastable and can tunnel to another state later. A metastable state can produce the low-energy laws we observe for a long period, but a later transition can change those laws inside some region. Such a late transition could produce observable signatures if it happened inside our past light cone. The sensitivity of complex structures to small changes in numbers is a central point. Some numbers can be varied by small amounts without destroying all complexity. Other numbers have narrow ranges that allow chemistry and life. For example, the balance between the strong force and the electromagnetic force must allow the existence of both hydrogen and heavier elements. A shift outside a certain range can eliminate either hydrogen or heavy elements. Without hydrogen, stars and many chemical processes cannot proceed. Without heavy elements, planets and complex chemistry are limited. The formation and fate of stars is tied to the strength of gravity and to the availability of cooling processes. Gravity pulls gas together. Cooling lets gas lose energy so it can collapse. Electromagnetic interactions and atomic transitions provide the main cooling channels. If those channels change because of different atomic structures, gas may not collapse in the same way. Star formation can be suppressed or altered. The lifetime of a star depends on how fast nuclear reactions proceed and on how gravity compresses the star. If the gravity number is larger, stars are denser and their nuclear fuel can be used faster. That leads to shorter lifetimes. If gravity is weaker, stars may burn more slowly, or they may fail to ignite at all if the pressure and temperature do not reach the needed thresholds. The production of heavy elements in stars requires a chain of nuclear reactions that are sensitive to the strong force and to particle masses. Planets and chemistry depend on the formation of heavy elements and on the structure of atoms and molecules. If stars fail to produce heavy elements, the material needed for rocky planets is absent. If chemistry is too limited because of altered atomic structure, complex molecules required for life will not form. The state inside the bubble thus directly affects whether planets and complex chemistry arise. These links explain why scientists take seriously the question of why our state has the numbers we measure. If the set of possible states is large, only a fraction will allow the sequence from particles to atoms to stars to planets. Observers can arise only in bubbles where that full chain works. This point does not answer why our state has the numbers it does. It does explain why only some states are compatible with observers. The technical route that links a field value to numbers often works through effective parameters. At high energy, the underlying theory may include many fields and many couplings. When some fields take fixed values, the low-energy theory can be described by a smaller set of numbers. That low-energy set is what experiments and observations measure. Calculating those low-energy numbers from the high-energy state requires a chain of steps. The details involve the interactions among fields and the way heavy particles decouple. In plain language, the high-energy choice determines which particles remain light, which couplings are large or small, and which symmetries are broken. The result is a definite low-energy world. Different high-energy states can therefore map to very different low-energy laws. In some mappings, small changes at high energy produce small changes at low energy. In other mappings, small changes at high energy can cause large shifts in low energy behavior. This model dependence is why theorists study many different high-energy constructions. They want to know which low-energy features are robust and which are fragile. One final point concerns the range of possible field values. Some potentials are shallow and allow the field to sit at many nearby values. Other potentials have deep minima that favor specific values strongly. When a minimum is wide and shallow, small quantum fluctuations can produce a range of nearby outcomes. When a minimum is deep and narrow, the state is more rigid and less variable. The shape of the potential thus affects how diverse the low-energy outcomes can be. All of these considerations show that the physics inside a bubble can differ in many ways. The differences can be small numerical shifts in a few constants. They can be large structural changes that remove whole classes of particles or forces. They can change the number and shape of spatial directions. The differences that matter most are those that affect whether bound structures can form and survive. Understanding how a state sets the low-energy laws is the bridge to the next question. Once we know which numbers are fixed and how they can vary, we can ask what structures can build from those numbers. The following step is to trace how particles combine into atoms, how atoms form gas and dust, how gas collapses into stars, and how stars produce the elements that make planets. That path shows how the choices made by a state lead to the large-scale content of a bubble. The numbers and rules set by a state decide which structures can form inside that bubble. Those rules tell whether particles bind, whether gas cools, and whether gravity can gather matter into stars and galaxies. This chapter explains the full chain from particles to complex structures. I use simple words and short sentences. First, a basic set of particles must exist. In our bubble, the most important particles for chemistry are electrons, protons, and neutrons. Electrons carry negative charge. Protons carry positive charge. Neutrons carry no charge. Protons and neutrons make atomic nuclei. Electrons orbit the nuclei and form atoms. If a state does not allow light-charged particles, atoms may not form. If charged particles have very different masses or charges, atoms may behave very differently. The first stage is atomic formation. In the early history of a bubble, matter and radiation are hot and mixed. As the bubble expands and cools, the temperature drops. When the typical photon energy falls below the binding energy of hydrogen, free electrons can join protons and form neutral hydrogen atoms. In our bubble, this happened about 300,000 years after the start of the hot phase. The ancient light that we call the cosmic microwave background comes from that time. If the binding energy of the simplest atom is different, the temperature at which atoms form changes. That change shifts when the ancient light decouples from matter. The behavior of gas depends on atomic and molecular physics. Gas can cool by emitting light. At high enough temperatures, atoms become excited and then emit photons when they drop to lower energy states. Molecules can emit light by rotating or by changing vibrational levels. Some atoms and molecules are especially good at radiating away energy. These radiative processes let gas lose thermal energy. If gas can lose energy, it can collapse under gravity to form dense clouds. If gas cannot cool efficiently, pressure can prevent collapse. The first gas that fills a newly formed bubble may have only the lightest elements. Big Bang nucleosynthesis in many cases produces mainly hydrogen and helium. Those two elements provide some cooling channels, but they are not as effective as heavier elements at low temperatures. Heavy elements, which astronomers call metals, form later inside stars. When stars create and release heavy elements, the cooling efficiency of the gas increases. That change allows smaller and more complex structures to form later. Gravity is the force that draws matter together. The strength of gravity in a bubble controls how fast and how strongly matter clumps. If gravity is very weak, matter takes a long time to gather. If gravity is very strong, matter can collapse too quickly and burn its nuclear fuel fast. The right balance is needed for stable, long-lived stars. Gravity also acts on dark matter if that form of matter exists. Dark matter is matter that does not interact much with light but still creates gravity. Dark matter can form the gravitational wells where gas collects. If there is no dark matter, the pattern of galaxy formation can be quite different. The next step is star formation. Dense pockets of gas collapse under their own gravity. As gas collapses, the pressure and temperature in the core rise. When the core reaches conditions that allow nuclear fusion, a star lights up. Nuclear fusion fuses light elements into heavier ones and releases energy. The balance between gravity pulling inward and radiation pushing outward sets the lifetime and the structure of the star. More massive stars have higher core temperatures. They fuse faster and burn out sooner. Less massive stars burn more slowly and can live much longer. Stars are the factories of heavy elements. In their cores, stars fuse hydrogen into helium. In later stages, heavier elements build up by successive fusion steps. Very massive stars can make elements up to iron by fusion. Elements heavier than iron form in explosive events where neutrons are abundant. Supernovae, the explosive deaths of massive stars, eject heavy elements into space. Neutron star mergers also eject heavy elements. Those heavy elements join the gas and dust in the interstellar medium. They become the raw material for future planets and complex chemistry. Planet formation depends on the availability of heavy elements. When a star forms, a disk of gas and dust often surrounds it. Dust grains are tiny solid particles that contain heavy elements. Those grains collide and stick together. Over time, they form larger bodies. Planets form from these larger bodies. Rocky planets need metals to build solid surfaces. Gas giants require a large amount of gas and enough solid cores to capture the gas. If heavy elements are rare in a bubble, rocky planets may be scarce or absent. Chemistry requires stable atoms and a range of elements. Chemical bonds form when electrons occupy orbitals around nuclei. The patterns of chemical bonds depend on the electron mass and the strength of the electromagnetic force. If electron mass or charge values change, the energies of bonds change. Some molecules may not be stable, others may form more easily. The variety of molecules that can exist in a bubble determines whether complex chemistry is possible. Complex chemistry sets the stage for structures that can store information and for processes that can support life as we know it. Time is an important factor. Stars need time to produce heavy elements. Planets need time to form from disks. Biological processes, if they arise, need time to develop complexity. The expansion rate of the bubble and the vacuum energy affect how long structures can grow. If the vacuum energy is large and positive, the background expansion can speed up and dilute matter before it can clump. If expansion is too rapid, gas will not gather into the halos needed to form galaxies. If vacuum energy is small or negative, the expansion pattern differs and the time available for structure growth changes. Small initial density variations seed structure. Tiny differences in density grow under gravity. The amplitude of these initial fluctuations affects how quickly matter collapses into halos. If the initial variations are too small, structures grow slowly. If they are too large, collapse can be rapid and chaotic. The scale and amplitude of these variations are linked to the inflationary processes that made the bubble. Thus, the early field dynamics indirectly affect later structure formation. The stability of nuclei matters. The mass difference between protons and neutrons helps set which nuclei can form and remain stable. If the proton were heavier than the neutron by a large amount, hydrogen might not be stable. If neutrons were too heavy or too light relative to protons, the mix of elements produced during early nucleosynthesis and inside stars would change. The existence of long-lived hydrogen and a range of heavier elements depends on these mass relations. The strength of the electromagnetic force also influences star behavior. That force governs how electrons bind to nuclei and how photons interact with matter. If the electromagnetic strength is different, the opacity of stellar material changes. Opacity affects how radiation travels out from the core. That in turn affects the star structure and the rate of fusion. The balance of forces inside stars is therefore sensitive to a set of numbers that the state fixes. Molecular cooling can be crucial for the first stars. Simple molecules can remove energy from gas and allow it to collapse to smaller masses. In gas that lacks molecules, stars that form may be very massive. Massive stars live shorter lives and explode sooner. In gas with molecules and later with heavy elements, smaller stars form. Smaller stars can live much longer and provide stable environments for planets. The existence of stable orbits for planets around stars depends on the gravitational and orbital dynamics set by the laws inside the bubble. Planetary orbits require that the central star is stable and that perturbations do not quickly eject planets. The mass and lifetime of the star must allow a long period in which planets remain at suitable temperatures for chemistry. The range of safe orbital distances depends on the star luminosity and on the radiative properties of the planet atmosphere, which in turn depend on chemistry. Galaxies assemble from many stars and from gas. In many cases, a central gravitational potential hosts many stars and clouds of gas. The shapes and sizes of galaxies depend on how matter falls into the halos created by dark matter or by baryons if dark matter is absent. The rate of star formation and the efficiency of cooling set the appearance of galaxies. Some bubbles may form only diffuse systems with little structure. Others may build large, dense galaxies. Magnetic fields and turbulence in gas affect star formation. Magnetic fields influence how charged particles move and how angular momentum redistributes in collapsing clouds. Turbulence can create dense clumps that seed star formation. The presence and strength of magnetic effects depend on whether the state permits long-lived charged particles and on the conductivity of the plasma. Radiation backgrounds influence chemistry and star formation. High levels of ultraviolet radiation can break molecules and ionize atoms. A strong radiation background can suppress molecular cooling. A quiet radiation environment allows molecules to survive and cooling to proceed. The level of background radiation depends on the population of luminous sources and on the transparency of the medium. The formation of heavy elements also influences the habitability of planets. Elements such as carbon, oxygen, nitrogen, silicon, and iron are essential for rocky planets and for chemistry. The supply of these elements depends on the history of star formation and stellar explosions. If a bubble has few massive stars, or if massive stars do not explode and release their elements, the enrichment of the gas can be slow or limited. Different choices of the basic numbers produce different outcomes. If gravity is much weaker, gas may not collapse into stars before the universe expands too far. If gravity is stronger, stars may burn out quickly and heavy element production may be rapid but short-lived. If the electromagnetic force is much stronger, atomic sizes and bond energies change. If it is much weaker, atoms may be fragile or chemistry may be limited. If the strong force is weaker, nuclei may not bind well and heavy elements may be rare. If the strong force is stronger, nuclear reactions in stars change. If the vacuum energy is too large, matter does not clump enough to form galaxies. Some changes produce extreme outcomes. If atoms cannot form, there is no chemistry. If stars cannot ignite, there is no stellar nucleosynthesis. If heavy elements never appear, rocky planets and complex chemistry are absent. In such bubbles, the structures that we call galaxies, stars, and planets may not exist or may be very different. The sequence from particles to observers therefore depends on several linked conditions. There must be particles that can form atoms. Gas must cool to allow collapse. Gravity must be strong enough to gather matter, but not so strong as to destroy long-term stability. Stars must make heavy elements and release them into space. Planets must form from the heavy elements. Chemistry must be rich enough to build complex structures. Time must be long enough for these steps to unfold. Scientists study these requirements by changing one number at a time in models. They test how star formation responds and how nucleosynthesis changes. They run simulations that follow gas collapse and star formation in different physical settings. These studies show which features are fragile and which can vary while still allowing structures. The studies also show that many small changes can add up. A small shift in particle mass can alter atomic energy levels. That shift can change the cooling rate of gas. A different cooling rate changes the typical mass of stars. Different star masses change the rate of heavy element production. That rate changes the availability of solids for planet formation. The chain is sensitive because each step feeds into the next. This sensitivity gives a reason why our bubble's specific numbers matter. The set of rules inside a bubble must allow a long sequence of successful steps. Only some ranges of numbers allow such a sequence. In bubbles where the rules fall outside those ranges, complex structures do not develop. Observations inside our bubble inform these models. We measure atomic spectra, nuclear reaction rates, stellar lifetimes, and galaxy properties. We measure the abundance of elements in stars and in gas. Those measurements help us understand which physical conditions lead to the structures we see. They also provide benchmarks to test how changes in the underlying numbers affect outcomes. The diversity of possible outcomes across bubbles is large. Some bubbles will form simple systems with only light elements and a few massive stars. Some will build many small stars that live for a long time. Some will never form stars at all. Some will form stars and planets, but in a form that does not support chemistry as we know it. The role of initial conditions and random processes is also important. Even with the same basic numbers, the exact timing of star formation and the distribution of heavy elements can vary. Random fluctuations in density affect which regions collapse first. The merger history of galaxies affects star formation rates. Supernova explosions can drive gas out of small systems and halt further star formation. These stochastic processes add variation on top of the underlying physical laws. All of this shows how the choices made by a state shape the physical world inside a bubble. The numbers set by the state define whether the full chain from particles to planets can occur. They set the pace and the pattern of structure formation. They shape the chemical inventory and the timescale available for complex processes. Bubbles that allow the chain from atoms to planets are the ones where many observers could arise. That fact is part of why scientists ask about the range of possible states. It also motivates searches for signatures that can reveal whether other bubbles exist or have affected our region. If a bubble collided with ours, the collision could change local field values and disturb this chain. The next topic examines how bubbles can meet and how such meetings can alter the structures that form inside a bubble. When a bubble meets another, the meeting can change the field values and the energy in the region where they touch. That change can alter the local laws that govern particles and forces. The meeting can also send out disturbances that travel through space. These processes determine what signatures a collision leaves inside a bubble. A bubble has a wall. The wall is a narrow region where the field moves from one value to another. The wall carries energy. When two walls collide, that energy must go somewhere. The energy can convert into motion of the fields, into particles, into heat, and into waves in space. The exact conversion depends on the values of the fields on each side and on how energetic the walls are. Collisions can happen at different times during the life of a bubble. A collision can occur early, while the field inside a bubble is still evolving and while the interior may still be inflating. A collision can happen later, after the field inside the bubble has reheated into particles and a hot plasma. The timing controls which physical systems the collision affects. If a collision happens early, it can change the initial conditions for the whole interior. If it happens later, it can affect only a limited volume of matter and radiation. When a wall hits another wall, the fields in the meeting region can be pushed away from their original values. The force from the collision can move the field over barriers in the potential. That motion can lead the region to settle into a different state than the surrounding area. The collision can create a patch inside the bubble where the effective low-energy rules differ. If that patch survives, it can become a region with different particle masses or different force strengths. The field motion after a collision can also produce oscillations. The field can roll or oscillate around a new local value. Those oscillations behave like a source of energy. They can decay into particles of different types or into radiation. If they decay into light particles, the collision can heat the local plasma. That local heating can leave a bright patch in the radiation field that later becomes the ancient light seen across the sky. The geometry of the meeting matters. If a collision happens along an extended boundary, the region affected inside a bubble has a definite direction. From the point of view of an observer inside the bubble, the collision creates a preferred direction on the sky. The region affected may appear as a disk or circle. The edge of that disk often has a sharper change than the interior. The disk center marks the direction toward the collision. A collision that happens before the time when the ancient light decoupled from matter can change the pattern of that light. The ancient light carries the record of conditions at the time of decoupling. If a collision altered the temperature, density, or the ionization state of the plasma in a patch, that patch will imprint a localized feature in the ancient light. The imprint can be a temperature shift or a change in the orientation pattern of the light. The imprint often has a circular or disc-like shape because the surface from which the ancient light last scattered intersects the causal region set by the collision in a circle. Polarization of light is another important signal. Light waves have an orientation. Scattering by free electrons can produce a preferred orientation. If a collision causes anisotropic flows or changes in the local quadrupole of the radiation field, it can produce a distinct pattern of polarization in the affected patch. The polarization pattern can help distinguish a collision imprint from ordinary random variations because it carries directional information about the perturbation. Collisions can also produce waves in the fabric of space. These waves are gravitational waves. A strong collision moves large amounts of energy and the mass distribution rapidly. That motion produces ripples in space that travel outward at the speed of light. The frequency and strength of these ripples depend on the typical size of the collision region and on how energetic the wall motion was. Very energetic collisions produce stronger ripples and higher peak frequencies. Different instruments are sensitive to different frequencies of gravitational waves. Detectors on Earth are tuned to comparatively high frequencies that come from small and fast sources. Networks of rapidly rotating astronomical clocks can probe very low frequencies that come from very large and slow processes. Detectors placed in space are sensitive to intermediate low frequencies. A collision can produce signals across a wide frequency range, but whether we detect them depends on the energy scale and the timing of the event. Besides waves and radiation, a collision can leave long-lived relics. The meeting can create defects in the field configuration that do not decay quickly. These defects include extended walls, lines, or localized lumps in the field. If such defects survive until late times, they can affect the motion of matter or light. A long, thin defect that crosses a region can change the paths of particles and light rays. A localized lump can act as an extra source of gravity. A collision can also inject new particles into the local medium. If heavy particles are produced and survive long enough, they add to the matter content. If they decay later, they release energy that changes the thermal history of the region. Late energy release can change the shape of the radiation spectrum. The ancient light has a very specific thermal spectrum. Small energy injections after a certain time can create slight distortions of that spectrum. Instruments that measure the spectrum with high precision can search for such distortions. The effect of a collision on structure formation depends on the time and the strength of the event. A collision that heats a patch of matter early can smooth out density contrasts there and delay collapse into stars and galaxies. A collision that increases density in a region can speed up collapse and create an overdensity that forms stars earlier. If a collision changes the local field values in a way that alters particle masses or force strengths, the chemistry and the cooling properties of gas in that patch can change. That change can alter the entire sequence of star and planet formation inside the affected region. The chance that a collision produces a detectable signature depends on several factors. One factor is the rate at which bubbles form in the inflating background. If bubbles form very rarely, collisions are unlikely. If bubbles form often, collisions are more common. Another factor is the expansion rate of the background space. Rapid expansion can push bubbles apart faster than they can meet. A third factor is the energy difference between the states. Large differences create more energetic walls and more violent collisions. Small differences produce weaker disturbances. The relative orientation of the collision also matters for what an observer sees. If the region affected by the collision lies within the past light cone of the observer, then some signal can reach that observer today. Whether it is visible in the ancient light depends on whether the intersection between the affected region and the surface of last scattering is large enough, and whether the contrast is strong enough compared to the ordinary fluctuations. If the affected region lies entirely behind or beyond the observable surface, no direct signal will appear in ancient light maps. A collision can produce a variety of temperature patterns in the ancient light. It can produce a hot spot or a cold spot, depending on whether the collision increased or decreased the local density or the local radiation temperature at the time of last scattering. It can also create gradients across the disk where the central part differs from the edge. The exact profile depends on the dynamics of the collision and on the time between the collision and the scattering surface. Polarization can show a characteristic radial or tangential pattern around the center of the affected patch. The change depends on how the collision changed local quadrupole anisotropies of the radiation field. Thus, a combined pattern of temperature and polarization can be a strong indicator that the feature came from a collision rather than from ordinary random processes. Gravitational waves from collisions can be stochastic or can appear as bursts. A burst is a single strong event that shows a sharp rise and fall in the detector. A stochastic background is a persistent, weak signal that comes from many events or from a continuous process. The character of the wave signal depends on how many collisions occur across the inflating background and on the distribution of their energies. Topological defects created or left behind by collisions can affect observations in several ways. A long defect that crosses the line of sight can produce a localized step in the temperature of the ancient light or a pattern in the polarization. A network of defects can add power to gravitational waves at certain scales. Defects can also influence the motion of galaxies and can show up in maps of the large-scale distribution of matter. Theoretical models predict different kinds of collision outcomes. In some models, the collision simply releases a burst of radiation that quickly redshifts away and leaves only a small imprint. In other models, the collision shifts the field into a new local minimum and creates a long-lived domain that has different constants. Some models predict that collisions generate clear rings in the ancient light. Others predict that collisions leave more complex and asymmetric shapes. The variety of theoretical possibilities makes the search challenging. Computers play an important role in predicting collision signals. Simulations follow the field dynamics and the expansion of space. They show how walls move, how fields oscillate, and how energy converts into radiation and particles. Simulations also track how a collision would affect radiation that later scatters and travels to us. By creating many simulated signals, scientists build templates that can be compared to observations. Templates help to find weak patterns that would be hard to see by eye. Observations face several limits. Foreground emission from our galaxy and from other sources can hide a collision signature. Instrument noise and calibration errors can create spurious features. The natural randomness in the ancient light produces patches that can mimic a collision signal by chance. To claim a detection, scientists must show that a feature is unlikely to arise from known sources and from random fluctuations. Cross-checks between different kinds of observations strengthen a claim. If a disk-like feature in the ancient light aligns with an unusual pattern in the distribution of galaxies in the same area, the case becomes stronger. If a gravitational wave detector sees a burst from a direction that also shows a feature in the ancient light, that alignment would be highly informative. A spectral distortion that matches the energy expected from a collision in the same patch adds further support. Multiple coincident signals reduce the chance that the observation is a false alarm. The distance to the collision event affects its angular size on the sky. A collision that affected the region near the surface from which the ancient light last scattered produces a small angular disk. A collision that affected a region nearer to us produces a larger angular disk. The angular size therefore tells us about the time and distance of the event relative to the scattering surface. Extracting that information requires careful modeling of the bubble geometry and of the expansion history of the interior. The velocity of the wall during collision matters too. Walls typically move at near the speed of light. When two walls meet at high speed, the energy density in the meeting region can be very large. That energy can produce high-frequency gravitational waves or prompt particle production. Slower or less energetic collisions produce gentler outcomes that are harder to detect but may leave relics that persist. Some collisions can change the curvature of the local region. The curvature affects the paths of light and the way large-scale geometry appears to observers. A collision that modifies curvature can shift the apparent angular sizes of distant features in one direction on the sky. That effect can show up as an anisotropic distortion of distance measures across the sky. The impact on galaxy formation can be complex. A collision can push gas out of halos in one region and therefore reduce the rate of star formation there. It can compress gas in another region and accelerate star formation. The net effect depends on the local energy deposition and on the timing relative to the formation of the first stars and galaxies. Because collisions are physical processes, they obey conservation of energy and momentum. That constraint limits possible outcomes. The wall energy must go somewhere. If a collision produces a hot region, that region expands and mixes with the surrounding matter. If it produces a change in the field values, that change spreads outward at finite speed. The conservation laws help determine the profile of the disturbance. Finally, collisions are not guaranteed to leave clear, unambiguous marks. Many collisions may be too weak or too early to leave detectable traces. Some may occur in directions that lie outside our observable patch. Others may leave signatures that mimic ordinary astrophysical phenomena. The search, therefore, relies on looking for patterns that match the predictions of collision models and that survive tests against alternative explanations. The meeting of bubbles is a physical process that can reshape part of a bubble interior. It can change field values and the low-energy rules. It can inject energy that alters the thermal and ionization history. It can produce gravitational waves and long-lived relics. It can change the path of structure formation in a local region. One of the most direct records of an early collision is the ancient light that fills the sky. That light carries information about the conditions at the time it last scattered, and it can retain the marks left by a collision that affected those conditions. The ancient light that fills the sky keeps a record of conditions in the early universe. If a bubble collision changed those conditions before the light escaped, the collision can leave a mark in that light. The main place to look is the cosmic microwave background, the remnant radiation from when the universe first became transparent. What the cosmic microwave background is: when the hot early universe cooled enough, free electrons joined to nuclei and light began to travel freely. That moment left a glowing bath of photons across space. We call that bath the cosmic microwave background. It is very cold now. It has a smooth temperature of about 2.7 degrees above absolute zero, but it shows tiny variations on top of that smooth value. The variations in temperature are very small. The size of typical variations is about 1 part in 100,000 of the mean temperature. Those variations carry information about the density, motion, and gravitational potentials in the early plasma. They also carry the mark of any event that changed conditions before the light left the plasma. How temperature differences arise. The early plasma had matter and radiation tightly coupled. Pressure and gravity produced oscillations in that plasma. Regions of higher density could compress and then rarefy. The state of those oscillations at the time the light escaped appears as a pattern of hot and cold spots in the cosmic microwave background. 3 main processes set the temperature at the time of last scattering. First, the intrinsic temperature of the plasma sets an initial value. Second, the motion of the plasma produces Doppler shifts. If the plasma moves toward us, the light is bluer and appears hotter. If it moves away, the light is redder and appears colder. Third, the light climbs out of and falls into gravitational wells. That effect changes the observed energy of the photons. The combination of these effects makes the pattern we see. The role of polarization: light can be polarized. Polarization means the electric field of the light has a preferred direction. In the early plasma, scattering of light by free electrons produced linear polarization when the incoming radiation had a directional variation. The amount of polarization is small. It is typically a fraction of the temperature variation. But polarization carries distinct information. It tells us about the local motions and quadrupole patterns of radiation at the time of scattering. Polarization patterns can be broken into 2 kinds. Scientists call them E modes and B modes. E modes have a pattern that does not change under mirror reflection. B modes change sign under mirror reflection. In the early universe, E modes arise naturally from the same processes that make the temperature variations. B modes need either gravitational waves or the bending of E modes by intervening mass to appear. Collision signatures often predict a distinct E mode pattern tied to the temperature pattern. How a collision changes the ancient light. A collision can change the temperature, density, and velocity of the plasma in a region. It can change the ionization level by heating or by altering the local field values that control particle interactions. Each of these changes affects the radiation that later decouples. If a collision increased the density or temperature in a patch at the time of decoupling, that patch will show a hotter region in the cosmic microwave background. If the collision lowered the density or cooled the patch, that region will appear colder. If the collision induced bulk flow in the plasma, the Doppler effect can produce a temperature shift with a specific angular pattern. If the collision changed the ionization level, it can alter how much polarization that region produces. The geometry of the intersection. The ancient light we observe today comes from a spherical surface centered on us. That sphere is the surface at which photons last scattered. A collision affects a region inside our past light cone. The intersection of that affected region with the last scattering surface is often a circular disk on the sky. The edge of the disk is where the boundary of the collision-affected region cuts the spherical surface of last scattering. The appearance of that disk depends on the timing and on the geometry of the collision. If the collision happened early and affected the region near the last scattering surface, the disk can be small in angular size. If the collision happened later and affected closer matter, the disk can be larger. The center of the disk points toward the direction of the collision. Typical temperature and polarization profiles. Models of collisions predict several patterns. A simple class of models gives a roughly circular temperature profile with a smooth change from center to edge. The center may be hotter or colder than average. The edge often shows a sharper change. The precise shape depends on how the field values moved during the collision and on how much energy the wall carried. Polarization patterns are strongly linked to the temperature profile. A collision that changed the local quadrupole of the radiation field at last scattering tends to produce a ring of polarized light around the disk. The orientation of polarization in that ring can be aligned either radially or tangentially relative to the center. The sign and strength of the polarization pattern depend on the details of the collision dynamics. Why polarization matters for detection. Polarization is a powerful discriminator. Random primary fluctuations in the cosmic microwave background do produce polarization, but the combination of temperature and polarization predicted by a collision is distinct. If a disk-shaped temperature feature also shows the expected polarization pattern, the chance that it came from ordinary random fluctuations is much smaller. Therefore, polarization data are crucial for confirming a collision signal. How scientists search in maps. Scientists use full sky maps of the cosmic microwave background to search for collision signatures. These maps show temperature and polarization across the sky. The maps come from instruments that observe at multiple frequencies. Satellites have provided the cleanest full sky maps because they can see the whole sky and measure many frequency bands. Ground-based observatories and balloon experiments provide deeper maps over smaller regions. The first step in analysis is to remove foregrounds. Our galaxy emits radiation that contaminates the maps. Dust emits thermal radiation at higher microwave frequencies. Charged particles spiraling in the galactic magnetic field emit synchrotron radiation at lower frequencies. Free electrons scattering off ions produce free emission. Extragalactic sources add point-like emission. Because these foregrounds have different spectra across frequency, scientists use multi-frequency data to separate the cosmic microwave background from foreground emission. Careful component separation reduces foreground contamination. After cleaning, scientists mask the most contaminated regions. They also correct for the instrument's beam, which blurs the sky, and for the varying noise across the map. Instruments have different sensitivity in different directions and at different times. Accounting for these effects is essential to avoid false signals. Template matching and statistical tests. A common search strategy is template matching. Scientists build templates that represent the predicted temperature and polarization pattern from a collision. They slide those templates across the sky at many positions and with many sizes. For each placement, they measure how well the template matches the observed map. This match yields a likelihood or a statistic. To assess significance, scientists compare the measured statistic to what they would find in maps that contain no collision. They generate many synthetic skies using the standard cosmological model and the known instrument noise. These synthetic skies include the ordinary random fluctuations of the cosmic microwave background. Scientists then run the same template search on each synthetic sky and record the distribution of the statistic. If the statistic measured on the real sky lies far in the tail of the distribution from the synthetic skies, that indicates the feature is unlikely to be a random fluctuation. Bayesian model comparison provides another route. Scientists compute how well the collision model explains the data compared to the standard model without collisions. They include knowledge of the instrument and of the foregrounds. The comparison yields an odds ratio between the two models. If the odds ratio strongly favors the collision model, the feature is a candidate detection. The problem of false alarms and the look elsewhere effect, searching across the whole sky and across many template sizes, raises the chance of false alarms. Even random maps will produce some regions that match a template well by coincidence. The more templates and positions tested, the more likely one of them will appear significant. To avoid false claims, analysts correct for the look elsewhere effect. They compute the probability of finding a match at least as good anywhere on the sky. This global probability is what matters for assessing a discovery. Cosmic variance limits. For the largest scales on the sky, we have only one real sample. This limitation is called cosmic variance. It means that for angular scales comparable to the whole sky, the statistical uncertainty remains large because we cannot observe many independent realizations. Cosmic variance makes it difficult to claim very high significance for features on the largest angular scales. For collision searches, this puts a hard limit on how certain we can be about very large disks. Foregrounds and systematics. Foregrounds can mimic collision signals. Dust emission can produce localized temperature and polarization features. Point sources can appear as hotspots. Imperfect component separation or residual foregrounds can bias the template search. Instruments also have systematic errors. Beam asymmetries, calibration errors, and correlated noise can create spurious features in maps. To guard against these problems, analysts perform many tests. They examine multiple cleaned maps made by different methods. They split the data into independent halves and check that a candidate feature appears in each half. They vary the mask and the frequency range used for cleaning. They test for correlations with known foreground templates. Only features that survive these checks remain viable candidates. Examples and past searches. Full sky searches have been carried out on data from multiple missions. Early searches on data from one satellite produced candidate disks and a few unusual spots. One notable unusual region is the so-called cold spot in the southern sky. That cold spot received attention because it is larger and colder than typical fluctuations. Analysts tested whether it could be explained by a bubble collision. The evidence did not prove that it was a collision. Subsequent studies showed that ordinary statistical fluctuations or residual foregrounds could explain it. Later, more sensitive full-sky data improved the tests. Analysts used Bayesian template matching and found no compelling evidence for bubble collisions across the whole sky. The searches placed limits on how common strong collisions could be and on how large their amplitude can be if they exist. These limits depend on the specific models and on the assumptions about the template shapes. The role of polarization in recent work, polarization data have become a key part of the search. Some temperature features that looked interesting returned no matching polarization signature. In those cases, the lack of polarization reduced the likelihood that the feature came from a collision. Polarization measurements are harder because the polarized signal is weaker and because polarization foregrounds are more uncertain. Nevertheless, current polarization maps already improve the discrimination power and reduce false alarms. Combining multiple observables, a collision can affect other observables besides the cosmic microwave background. It can change the distribution of galaxies, produce spectral distortions, or generate gravitational waves. Combining evidence across different observables strengthens a claim. For example, a disk-shaped temperature feature that also aligns with a change in the large-scale distribution of galaxies and with a burst of gravitational waves would be a strong joint signal. Cross-checks like these require independent data sets and careful joint analysis, limits and room for future improvement. Current searches are limited by instrument sensitivity, foreground removal, and cosmic variance. The cosmic microwave background remains a powerful probe because it records early conditions directly. Future instruments with lower noise and better control of systematics will improve the sensitivity, especially in polarization. Ground-based observatories that map large fractions of the sky and new satellite missions with more frequency channels will reduce foreground uncertainty. Better simulations are also essential. Simulations that include realistic foregrounds, instrument effects, and many realizations of collision models help set accurate detection thresholds. They allow analysts to understand how often false alarms appear and how different systematics affect the results. Why a clear detection is difficult. A clear detection requires a feature that is strong enough to stand out from the ordinary fluctuations, and that shows the expected polarization and other correlated signals. Many possible collision outcomes are weak and produce subtle imprints. Some collisions may lie partly or wholly outside our observable region. Some may have occurred so early or so weakly that their marks were erased by later processes. All of these possibilities reduce the chance of a clear signal. A detection must also survive scrutiny about foregrounds and instrument systematics. Analysts need to show that the feature cannot be explained by dust, point sources, or map-making errors. Tests that split the data and compare independent instruments are important to build confidence. The promise of polarization and joint probes. Polarization gives an extra handle on the physics. The predicted link between temperature and polarization in a collision reduces the chance that a random fluctuation can mimic the full signature. Adding information from galaxy surveys, spectral measurements, and gravitational wave observatories further tightens the case. Together, these probes offer a path to increase confidence in any claim. A collision can also produce gravitational waves and other dynamic signals. Those signals travel through space and can be measured by different kinds of detectors. The pattern left in the cosmic microwave background is only one way a collision announces itself. Gravitational waves and other time-dependent signals provide complementary information about the energy and timing of the event. Those moving signals send out information that can reach instruments and observatories. One main kind of moving signal is a gravitational wave. I will explain what gravitational waves are, how bubble dynamics can make them, and how we try to detect them. I will also describe other dynamic signals that collisions and field motion can produce. I will keep the language simple and direct. What a gravitational wave is. A gravitational wave is a disturbance in space that makes distances change briefly. The disturbance moves through space at the speed of light. As a gravitational wave passes, the distance between 2 points can stretch and then shrink. The effect on any one distance is extremely small. Sensitive instruments are needed to measure these tiny changes. Gravitational waves are produced by moving energy and mass. When mass or energy shifts in an asymmetric way and does so rapidly, it emits gravitational waves. Stronger changes in the distribution of energy produce stronger waves. Rapid changes produce waves with higher frequency. The details of the source set the overall strength and the frequency range of the waves produced. How bubble dynamics produce gravitational waves. Bubble walls carry energy. When walls move, collide, or oscillate, that energy changes its distribution in space. Rapid motion of the walls produces gravitational waves. A collision between two walls sends a large directional disturbance into the interior regions. Oscillations of fields after a collision can continue to produce waves for some time. Turbulence in the plasma created by reheating can also generate gravitational waves. The total wave output depends on how energetic the walls are and on how much of the energy is converted into motion rather than into immediate particle production. Different stages of bubble dynamics give different kinds of wave signals. A single strong collision can produce a burst of waves that arrives over a short time. Many collisions across the inflating background can produce a persistent background made of many overlapping bursts. Ongoing oscillations and turbulence can produce a stochastic signal that lasts for a long time. Topological defects left behind by field dynamics can produce a continuous or slowly changing wave signal. Frequency ranges and detector types. The frequency of a gravitational wave relates to the timescale of the source. Short, rapid events give higher frequencies. Long, slow processes give lower frequencies. Different instruments are sensitive to different frequency ranges. A full search for signals from bubble dynamics therefore needs many kinds of detectors. Ground laser interferometers are sensitive in a frequency band from about 10 Hz to about 1000 Hz. These instruments measure tiny changes in the distance between mirrors separated by several kilometers. Examples of operating ground detectors include LIGO, Virgo, and KAGRA. They detect short bursts from compact object mergers and other fast events in that band. Space-based laser interferometers aim at lower frequencies, roughly from 1 mHz to 1 Hz. The long arm lengths in space make the instruments sensitive to slower, larger-scale motions. A space interferometer can probe signals that ground detectors cannot reach because of seismic noise and other disturbances on Earth. Pulsar timing arrays probe even lower frequencies. They measure time shifts in the arrival of pulses from many stable radio pulsars. The timing changes produced by gravitational waves at frequencies near 1 cycle per year to 1 cycle per decade can be detected by looking for correlated timing residuals across the sky. Pulsar timing arrays gather data over many years to build the needed sensitivity. Very low-frequency gravitational waves, with periods longer than the age of the visible universe at last scattering, can leave a signature in the polarization of the ancient light. Those waves alter the pattern of polarization on the largest angular scales. Cosmic microwave background polarization experiments search for these signatures. How signals are classified. Scientists separate gravitational wave signals into a few broad classes. A burst is a single short event that produces a clear rise and fall in the detectors. A continuous source produces a nearly steady oscillation over a long time. A stochastic background is the sum of many unresolved sources that produces a random but persistent signal. Each class needs a different search method. For a burst, analysts search for short transients in the detector time series and for consistent signals in multiple detectors. For a continuous source, analysts search for steady oscillations with a narrow frequency. For a stochastic background, analysts compute cross-correlations between detectors to find common signals buried in noise. detection methods, and data analysis. Ground and space interferometers use laser interferometry to measure changes in distance between test masses. The devices record a strain time series that encodes how distances change. Analysts use pattern matching when a template for the signal is known. This method is called matched filtering. For well-modeled signals, matched filtering maximizes sensitivity. When signals are not well modeled, analysts use more general searches that look for excess power or for coherent structure across detectors. For a stochastic background, cross-correlation filters between pairs of detectors are the standard method. Cross-correlation builds on the fact that a gravitational wave signal will produce correlated responses across separated instruments, while instrument noise will not be strongly correlated. Pulsar timing arrays use a different method. They measure pulse arrival times from many pulsars and build timing residuals by subtracting a precise timing model. A gravitational wave background will induce correlated timing residuals with a specific angular pattern across pairs of pulsars. Analysts compute the cross-correlation matrix and test whether it matches the expected pattern. Cosmic microwave background experiments search for B-mode polarization at large angular scales. A primordial gravitational wave background or other very low-frequency waves can source this mode. Analysts use maps of polarization and compute power spectra and other statistics to find the imprint of gravitational waves. Modeling and simulations. To design searches and to interpret data, theorists and numerical modelers produce predictions for the waveforms and for the spectral shape of the background. For bubble collisions and field dynamics, the problem is nonlinear. Numerical simulations follow the evolution of fields and the expansion of space. They compute the motion of walls, the conversion of field energy into particles, and the associated emission of gravitational waves. Simulations must resolve a wide range of scales. They are computationally costly. Many runs across model parameters are needed to explore the space of possible signals. Simplified analytic formulas can guide the intuition and the scaling relations. Both simulations and analytic work feed into the templates and into expectations for frequency and amplitude. Other dynamic signals beyond gravitational waves, bubble dynamics can produce other moving signals. Collisions and reheating can create particles with high energies. Those particles can later decay and produce gamma rays, cosmic rays, or neutrinos. If heavy particles are produced and survive long enough, they can affect the matter content and the thermal history of the region. Late energy release can create distortions in the spectrum of the cosmic microwave background. The background light has a nearly perfect thermal shape. Small injections of energy at particular times produce characteristic departures from that shape. Instruments that measure the spectrum with high precision can search for these small distortions. Field oscillations and relic fields can also leave imprints on the motion of matter or on the values of fundamental constants. If a relic field couples to ordinary matter, it can produce small time-dependent shifts in masses or in coupling strengths. Precision laboratory experiments and atomic clocks can probe tiny changes in constants over time. Topological defects and long-lived relics. Field dynamics after collisions can create topological defects. A domain wall is a two-dimensional sheet where the field changes from one value to another. A cosmic string is a one-dimensional line of concentrated field energy. A monopole is a localized lump. These defects carry energy and can move through space. Defects produce gravitational waves as they move and as segments oscillate. A network of defects can produce a continuous stochastic background. The spectrum depends on the defect properties and on how the network evolves. Defects can also lens light, affect particle motion, and seed localized gravitational effects. Detection challenges and foregrounds. Detecting gravitational waves and other dynamic signals faces many obstacles. Instruments have noise. Ground detectors face seismic noise, thermal noise, and technical noise from the instrument. Space detectors face noise from disturbances of the spacecraft and from laser frequency noise that must be controlled. Pulsar timing arrays face noise from the pulsars themselves, from radio frequency interference, and from errors in modeling the solar system ephemeris. Astrophysical sources produce foreground gravitational waves. Compact binary mergers, rotating neutron stars, and a population of unresolved binaries create a background that can mask cosmological signals. Separating a potential signal from bubble dynamics from the astrophysical background requires a model for both and a search that exploits differences in spectral shape, anisotropy, and other features. Pulsar timing arrays face an extra challenge. The same population of supermassive black hole binaries that produce a stochastic background in the pulsar timing band is the main expected astrophysical background. Distinguishing a cosmological signal from this astrophysical background requires measuring the angular correlation pattern and the spectral slope precisely. Methods to separate signals. Analysts use several properties to separate signals. Frequency content helps. A cosmological source may peak at a different frequency than the dominant astrophysical background. The shape of the spectrum across frequency gives a diagnostic. Directional information helps. A gravitational wave background that is isotropic differs from a foreground dominated by nearby sources that produce anisotropy. Polarization and statistical properties also help. Some cosmological processes produce non-Gaussian features or a polarized gravitational wave background. Astrophysical backgrounds are often closer to Gaussian when many unresolved sources overlap. Time dependence and association with electromagnetic signals provide extra tests. A burst that aligns in time and direction with a gamma ray or neutrino signal tightens the identification. The role of joint observations across detectors and across messenger types are powerful. A gravitational wave burst observed in ground detectors that also has a correlated transient in gamma rays or neutrinos allows a more secure identification of the source. A stochastic background detected in pulsar timing that shows the expected angular correlation pattern gains confidence from coincident results from other pulsar arrays. Combining gravitational wave searches with maps of the ancient light and with surveys of galaxies adds further power. A feature in the cosmic microwave background that points to a particular direction can guide gravitational wave searches for a burst from that region. If a spectral distortion points to energy injection at a particular time, gravitational wave spectra can be compared to the timing implied by that injection. Recent developments and experimental hints. Gravitational wave astronomy has matured rapidly. Ground detectors have detected many compact binary mergers. Those detections show that precise measurement of waveforms is possible. Pulsar timing groups have reported a common spectrum process in their datasets in recent years. That signal may be a gravitational wave background. Analysts continue to test whether the spatial correlations expected for gravitational waves are present in the data. The question remains under active study. Space mission concepts and future ground detectors will expand the accessible frequency range and improve sensitivity. Larger and more sensitive arrays of radio telescopes will improve pulsar timing precision. New cosmic microwave background polarization experiments will push limits on very low frequency waves. All of these efforts increase the chance of finding a signal that traces back to early bubble dynamics. What a detection would tell us, a gravitational wave signal from bubble collisions would provide a direct probe of the energy scales and of the dynamics of the early transitions. The spectrum gives information about the size and speed of walls, about the fraction of energy converted into motion, and about the timing of reheating. Other dynamic signals, such as particle bursts or spectral distortions, would add constraints on particle production and on the thermal history inside a bubble. Together, these dynamic measures would complement maps of the ancient light and of the large-scale structure. A joint detection across gravitational waves, the cosmic microwave background, and galaxy surveys would provide a coherent picture. It would allow scientists to connect the early field dynamics to later structure formation. Limits of the dynamic searches. Even with many detectors, some signals may remain undetectable. If collisions occurred at energy scales far below what instruments can probe, their waves will be too weak. If the main energy went into particles that thermalized quickly, the gravitational wave output may be small. If the dominant background at a given frequency is astrophysical and very loud, a cosmological signal at that frequency may be hidden. Nevertheless, the range of instruments across frequencies and messenger types gives multiple routes to search. Improvements in sensitivity, in modeling, and in joint analysis methods all increase the discovery potential. Final view. Dynamic signals such as gravitational waves, bursts of particles, and relic field oscillations provide direct probes of the energetic events that can occur when bubbles form and meet. Different detectors access different parts of the signal spectrum, and different messenger types add independent checks. The search for these signals requires accurate models, careful data analysis, and coordinated observations across instruments. These dynamic efforts work together with maps of galaxies and with precise spectral measurements of the background light to build a full search strategy for signs that our bubble has had partners or that the early field dynamics left enduring traces. Maps of galaxies and precise measurements of the background light give more ways to search for marks left by early bubble dynamics. These datasets probe different parts of the history of the universe. They probe different physical processes. Together they can test whether a collision or a change in field values altered the matter and radiation in one region. How galaxy surveys map the matter in space. Galaxies are bright objects we can see across great distances. A galaxy forms where matter has gathered. Over time, many galaxies form in regions where matter is denser. By mapping where galaxies lie, we build a map of where matter clustered in the past and where it clustered later. Surveys measure the positions of many galaxies across the sky. Surveys also measure the light from each galaxy. The light shows spectral features that are shifted by the expansion of space. That shift tells us the distance to the galaxy. With a distance and an angle on the sky, we can place the galaxy in 3 dimensions. A 3-dimensional map of galaxies shows how matter is arranged in volume. Some surveys measure precise distances by taking spectra of galaxies. Those are spectroscopic surveys. Other surveys measure colors in several bands and infer distances roughly. Those are photometric surveys. Spectroscopic surveys give better distance accuracy at the cost of observing fewer galaxies per unit time. Photometric surveys cover larger areas with many more galaxies, but with larger distance uncertainty. What the maps show in structure. The galaxy maps reveal patterns. On small scales, galaxies group into clusters. On larger scales, galaxies arrange in long strands and in empty regions. Scientists describe these patterns with statistical measures. One common measure asks how likely 2 galaxies are to sit a certain distance apart. This measure is the 2-point correlation function. Another description uses the power spectrum. The power spectrum shows how much clustering exists at different size scales. There is also a preferred scale imprinted early in the universe. That scale is the remnant of sound waves that moved through the early plasma. It appears as a bump in the correlation function. Measuring that scale helps calibrate distances across cosmic time. Surveys use this signal to measure how the universe expanded, how a collision could change the galaxy map. A collision or a local change in field values can change the initial conditions for structure growth in a region. If the collision increased the local density contrast at early times, matter in that region can clump faster and form more galaxies earlier. If the collision decreased the local density contrast, the region can form fewer galaxies. If the collision injected bulk motion, it can create coherent flows of matter in a preferred direction. The effect often has a directional character. A collision that affects a finite patch produces an imprint that is localized on the sky. The imprint in the galaxy distribution can appear as an excess or a deficit of galaxies in a disk-shaped area when seen from our viewpoint. The same patch may show altered clustering statistics when measured inside the disk compared to outside. A collision can also change the mass function of halos. Halos are the dark matter structures where galaxies form. By shifting the local amplitude of fluctuations, a collision can change the number of massive halos in a region. That change affects the number of large galaxies and of clusters. Observers can count clusters or bright galaxies in a patch and compare with expectations from standard cosmology to search for anomalies. Methods to search in galaxy surveys. One method is to compare galaxy counts in a candidate region with counts in similar regions elsewhere. Scientists build a distribution of counts from many patches and test whether the candidate region is an outlier. Another method stacks many similar candidate regions together. Stacking increases the signal-to-noise when each individual region has weak signal. Analysts also compute the correlation function inside and outside the patch. If a collision changed the clustering, the correlation function will differ. In addition, analysts look for anisotropic signals. A collision can produce a preferred direction in the velocity field. That direction can leave an imprint in redshift space. Redshift space distortions change the apparent clustering along the line of sight. Measuring the difference between radial and transverse clustering can reveal such an effect. Tomographic approaches use redshift bins. By slicing the galaxy sample into many distance intervals, scientists can see when an anomaly appears in time. If a collision occurred early, its imprint can appear in high redshift slices. If it happened later, it might appear only in low redshift slices. Tomography thus helps constrain the timing of an event. Cross-correlations with other maps. Cross-correlation compares galaxy maps with other observables. A common comparison is with maps of the ancient light. If a disk-shaped feature in the cosmic microwave background aligns with a deficit of galaxies in the same area, the joint evidence is stronger. Cross-correlation can also use maps of weak gravitational lensing. Weak lensing maps trace the total mass, not only the luminous galaxies. If a candidate region shows mass deficits or excesses in lensing maps, that supports the presence of a real mass anomaly. Cross-correlation with maps of hot gas gives other probes. Hot gas in clusters scatters the ancient light and produces a spectral shift signature in that light. That signature is the thermal Sunyaev-Zeldovich effect. If a collision affected the gas heating or the cluster abundance, the TSZ signal will change. X-ray maps from space telescopes provide complementary views of hot gas. A consistent signal across galaxy counts, lensing, TSZ, and X-ray supports a physical change in the region. Radio surveys and the 21-centimeter line, the neutral hydrogen atom emits a specific radio frequency when its electron flips spin. Astronomers call that the 21-centimeter line. Surveys of this emission probe the distribution of neutral gas, especially at early times when stars and galaxies were forming their first structures. Radio arrays can map the intensity of the 21-centimeter signal across large volumes. This method is called intensity mapping. A collision that changed the timing of heating or ionization can leave a clear imprint in the 21-centimeter signal. If a patch was heated early, the hydrogen signal there may be suppressed. If a patch remained colder, the signal will differ in the opposite sense. 21-centimeter measurements probe a wide range of redshifts that are otherwise hard to access. They therefore provide a powerful test for early energy injections or for local changes in heating and ionization histories. Weak lensing and mass mapping. Weak gravitational lensing uses the shapes of distant galaxies to measure the deflection of light by intervening mass. By measuring small distortions in many background galaxies, analysts reconstruct maps of the projected mass distribution. This mass map is independent of whether the mass is luminous. It therefore tests whether a region has a real mass excess or deficit. If a collision changed the initial clustering of matter, the weak lensing map will show a corresponding pattern. Lensing can reveal mass that has no visible galaxy counterpart. Combining lensing with galaxy counts separates baryonic effects from total mass effects. That separation helps identify whether a change came from altered baryonic physics or from a true change in the matter distribution. Spectral tests of the background light. The ancient light has a nearly perfect thermal spectrum. That means the intensity as a function of frequency follows a precise shape. Small energy injections change that shape in characteristic ways. Scientists classify those changes into different types. One type is often called mu distortion. This distortion arises when energy is injected at very early times, when photons and particles could still exchange energy efficiently but could not change their overall number quickly enough. The injected energy shifts the spectrum into a new equilibrium that has a non-zero chemical potential. Analysts call that a mu-type change. Another type is called Y distortion. This arises when hot electrons scattering photons transfer energy in a way that shifts the spectrum. The Y-type distortion shows a different frequency dependence from the Mu type. Energy injection at intermediate times tends to produce Y-type features. Late-time heating in clusters also produces Y distortions through the thermal Sunyaev-Zell dig. Bubble dynamics and collisions can inject energy. If a collision heated the plasma before the formation of atoms, it can produce a mu distortion. If the heating happened later, the result can be a Y distortion. The size of the distortion depends on how much energy was injected relative to the photon energy density at the time. Current and future spectral measurements. A past satellite instrument measured the spectrum of the ancient light with high precision. It found that the spectrum matches a thermal shape very well. This result places strong limits on how much energy could have been injected at certain times. These limits already rule out large energy releases from many processes. Future proposed missions aim to measure the spectrum with far greater sensitivity. Those missions would detect much smaller distortions. Detecting a mu or Y signature from a collision would give direct evidence of energy injection. The spectrum also provides timing information. The spectral shape helps locate when the energy was released. Searching for relics and defects, bubble collisions, and field dynamics can leave long-lived relics. These relics include extended defects, such as domain walls and cosmic strings. They also include localized lumps or unusual fields that remain after the collision. Cosmic strings are thin concentrations of field energy that can extend across large distances. If strings exist, they can produce several observational effects. A moving string can create sharp discontinuities in maps of the ancient light. Strings can generate gravitational lensing that shifts the apparent positions of background galaxies in a characteristic way. String loops oscillate and radiate gravitational waves, Pulsar timing arrays and gravitational wave detectors can search for the stochastic background produced by a population of strings. Domain walls are two-dimensional sheets of field energy. If a domain wall crosses our region, it can create anisotropic effects in the distribution of matter and in the ancient light. Large domain walls are constrained by observations because they would dominate the energy density or leave strong anisotropy. Small or rare walls are harder to rule out. Monopoles and other point-like relics would act as heavy localized objects. They can affect cosmic rays, lens light, or alter local gravitational fields. Laboratory searches and astrophysical surveys place limits on their abundance. Laboratory and astrophysical searches for new fields, relic fields that couple weakly to ordinary matter, can be searched for in the laboratory. Axion-like particles are a class of light fields that can couple to photons or to nuclear spins. Experiments that search for axions use resonant cavities, magnetized detectors, or precision magnetometers. Other experiments use atomic clocks and measurements of fundamental constants to probe slow changes that a relic field might cause. Astrophysical observations also constrain new fields. Stars and supernovae can emit light particles and thereby cool faster. Measurements of stellar evolution set limits. Observations of supernova neutrinos and of the light output constrain how much energy could go into unknown particles. How analysts compare data to models. To test a specific bubble or collision model, scientists simulate the expected outcome. They run simulations that produce mock galaxy catalogs, lensing maps, and spectral signatures for a given set of parameters. They feed these mock data through the same analysis pipeline used on real data. This forward modeling ensures that the same selection effects and observational issues are applied. Analysts then compare the observed data to the model predictions. They compute likelihoods or probabilities that the data arise under the model and under the standard model without any bubble effects. They use Monte Carlo methods to build distributions of the test statistics under each hypothesis. If the observed value lies far outside the distribution for the standard model, that supports the bubble model. Careful accounting for systematics is essential. Surveys have selection effects. Foreground emission from our galaxy can bias counts. Photometric distance errors scatter galaxies across redshift bins. Instrumental noise and calibration errors add spurious signals. Analysts must model these effects and include them in the simulations. Why multiple probes are important. A signal seen in one dataset can be created by mundane astrophysical processes. For example, a deficit of galaxies in one region can occur because of dust obscuration or because of survey incompleteness. A mass deficit in lensing maps can arise from shape measurement biases. A spectral distortion can come from improper calibration. Finding consistent signals across different probes reduces false positives. If a disk-shaped feature appears in the ancient light and the same disk shows a deficit in galaxy number counts and a matching mass anomaly in lensing maps, the combination is hard to explain by simple systematics. Joint analysis of independent datasets therefore strengthens discoveries. What these searches can reveal, surveys of galaxies and spectral measurements, expand the range of tests for bubble dynamics. They probe the matter distribution at many times. They can detect energy injections and relics that other probes miss. They help constrain the timing, energy scale, and the spatial pattern of candidate events. These methods require careful modeling and many cross-checks. They also need wide sky coverage and deep sensitive observations. When combined with maps of the ancient light, with gravitational wave searches, and with laboratory experiments, they form a comprehensive strategy to search for traces of other bubbles or of early field dynamics. These observational pathways are powerful. They also face limits. Observational noise, foregrounds, and the finite size of the observable universe set hard boundaries on what can be learned. Understanding these limits is necessary to judge what a null result means and what a robust detection would require. Even with many ways to look and many instruments working together, testing the bubble idea faces many hard limits. These limits come from the nature of the universe, from the instruments we build, from the sky we must observe, and from the theories we use to make predictions. This chapter explains those limits in simple words. I describe what they are, why they matter, and what they mean for the search. A first limit is set by what can send us information at all. Light and other signals travel at a fixed speed. The universe also expands. Because of that, some regions lie forever beyond the place that can send signals to us. If another bubble sits beyond that boundary, no signal from it can reach our instruments. This boundary is often called the cosmic horizon. The horizon is a hard physical limit. It stops us from learning about regions that lie beyond it. A second limit comes from the fact that we have only one universe to observe. For the largest patterns on the sky, we cannot measure many independent copies. This limit is called cosmic variance. It means that for very large angular scales, the uncertainty remains large because we have only one sample. No matter how good our instruments become, cosmic variance remains a flaw on how precisely we can measure the largest features. Signals themselves can be very weak. A bubble collision can leave an imprint that is small compared to the normal variations in the sky. Weak signals are hard to pull out of noise. Instrument noise can be reduced by making longer observations. Many repeated measurements lower random noise, but some sources of error do not shrink with more time. Those persistent errors are called systematic errors. Systematic errors arise from imperfect calibration of instruments, from how the instrument responds to the sky, and from effects that vary over time in ways that are hard to model. Foreground emission is a major source of confusion. Our galaxy contains dust and charged particles that emit radiation. Dust emits thermal radiation at microwave frequencies. Charged particles spiraling in magnetic fields emit radio waves. Other galaxies and active galactic nuclei add point-like sources. All these foregrounds live between us and the ancient light. They also affect maps of galaxy surveys and of radio signals. Foregrounds can hide real signatures or create patterns that look like the signatures we search for. Separating the cosmic signal from foregrounds requires observations at many frequencies and careful modeling of the foreground components. Ground-based instruments face additional limits from the atmosphere. The atmosphere emits and absorbs radiation. It also changes over time. Radio interference from human activity affects observations at many wavelengths. Observers must avoid some frequencies and must correct for variable atmospheric conditions. Observations from high and dry sites reduce these problems. Space instruments avoid atmospheric noise, but they cost more and take longer to build. Instrument beams are another limit. A telescope does not see a perfect point. It blurs the sky according to its beam shape. If the beam is not symmetric or if it changes with direction, that can imprint spurious features in maps. Correcting for the beam requires accurate beam maps and stable instrument operation. Imperfect beam correction can bias searches for localized signatures. Noise in detectors is not always pure random noise. Some noise has correlations across time or across detectors. Correlated noise can mimic large-scale features on the sky. Analysts must model correlated noise and include it in simulations. If they fail to model it correctly, they may find spurious detections or miss real signals. Statistical challenges are central. When scientists search the whole sky for a rare pattern, they perform many tests. Each test has a chance to produce a statistical fluctuation that looks like a signal. The more tests one runs, the higher the chance of a false alarm. This effect is called the look everywhere problem. To avoid false claims, analysts must correct for the number of trials. They must compute how likely it is to find a feature as extreme as the observed one anywhere in the search. A feature that looks unlikely in a single test can be likely when many tests are considered. Scientists use strong thresholds for claiming discoveries. They require very low probability that a feature arises by chance. For example, a chance of 1 in 1 million or smaller is often needed before a claim is taken seriously in fields that demand high certainty. Even then, the claim must pass many additional checks to exclude non-random causes. Model dependence is another important limit. Theoretical models of inflation and of bubble formation predict a wide range of outcomes. Some models predict sharp circular imprints, others predict weaker or more complex patterns. The variety of models means that a search tuned to one template may miss signatures predicted by another model. Conversely, a match to a specific template may not prove the underlying model is correct. Different physical processes can produce similar observable features. This degeneracy means that even a good match does not uniquely identify the cause. Simulations are needed to connect theory to observations. Simulations of bubble collisions must follow nonlinear field dynamics and the expansion of space. They must then propagate the effects into radiation and matter and into the observables we measure. Running these simulations at high resolution across a large range of parameters takes a lot of computing time. It also requires many runs to explore different field potentials and different collision scenarios. The computational cost limits how fully scientists can map the space of possible signatures. Astrophysical confusion is a major challenge. Many ordinary processes in our universe can create localized features. Galaxy clusters can produce spots in the ancient light through scattering of photons by hot electrons. Active galaxies can produce radio and microwave emission that looks like a small hotspot. Dust clouds can produce localized temperature and polarization features. Supernova remnants and other galactic structures can create emission that complicates maps. Without careful separation, these ordinary sources can mimic or mask the signatures of a bubble collision. For gravitational waves, strong astrophysical backgrounds exist. Compact binary mergers, rotating neutron stars, and a population of unresolved binaries produce gravitational waves across many frequencies. These astrophysical signals can dominate the band where a cosmological signal might live. Separating a cosmological background from astrophysical noise requires models for both and careful statistical methods. In some frequency bands, the astrophysical foregrounds may be unavoidably louder than the cosmological signal. Survey limits also matter for galaxy maps. No survey covers the entire sky at unlimited depth. Some surveys cover large areas with modest depth. Others probe deep, but over smaller patches. Survey selection effects, such as masking regions near bright stars or regions with high dust, can bias counts. Photometric distance estimates have errors that scatter galaxies across distance bins. Spectroscopic surveys give better distances but are slower and cover fewer objects. The finite number of galaxies in a volume leads to shot noise. Shot noise limits how well one can measure clustering on small scales. Redshift uncertainties limit how well one can place a structure in time. If distance errors are large, the signal from an anomalous region can be smeared across many redshift bins. This smearing reduces the contrast and makes detection harder. Tomographic analysis that slices data into many small redshift bins helps, but it also increases statistical noise in each bin. Spectral measurements of the ancient light face limits from instrument calibration and from astrophysical backgrounds. The thermal shape of the ancient light is known to high precision. That leaves little room for large distortions. Current limits already exclude large energy injections at many times in the past. Detecting very small distortions requires instruments with extremely stable calibration and with the ability to remove foreground emission to high accuracy. Building such an instrument is difficult and expensive. Another limit comes from degeneracy in signatures. A given observable pattern can result from more than one physical cause. A temperature disk in the ancient light could come from a bubble collision, or from an unusual cluster, or from a statistical fluctuation. A gravitational wave background with a certain spectrum could come from cosmic strings, from the first stars, or from bubble collisions. This degeneracy requires multiple lines of evidence to break. A single signature rarely suffices to identify the cause uniquely. Human and procedural limits exist too. Data analysis involves many steps. Choices about how to clean the data, how to mask the sky, which templates to test, and how to weight different regions can affect results. Analysts must avoid bias. Blind analyses help. In a blind analysis, scientists define their tests before looking at the part of the data where a signal might appear. Blind procedures reduce the chance of bias from conscious or unconscious choices. Reproducibility is essential. Independent teams using different instruments or different analysis methods must confirm a claimed detection. A signal that appears in one map but not in an independent map is suspicious. Open data and open code help other teams reproduce results. Publishing null tests and showing that the signal survives many checks increases confidence. Mitigations exist for many of these limits. Observing at many frequencies reduces foreground contamination because different sources have distinct spectral shapes. Cross-checking with independent instruments reduces the chance that a feature arises from instrument error. Polarization information adds constraints because many foregrounds have different polarization properties than the cosmological signal. Combining maps of galaxies and weak lensing with the ancient light allows checks that rely on independent physics. Simulations help to quantify how often random fluctuations or known foregrounds produce features like the ones searched for. Analysts inject fake signals into mock data and test whether the pipeline recovers them. These injection tests show the sensitivity and the false alarm rate. End-to-end simulations that include instrument response, foregrounds, and the cosmological signal allow analysts to estimate detection thresholds under realistic conditions. Statistical methods address multiple testing. Analysts compute the chance of finding as strong a feature anywhere in the search by generating many mock skies. This global significance corrects the false alarm rate for the number of trials. Bayesian model comparison adds another tool. It asks which model, among those considered, best explains the data while taking into account how complex the model is. Bayesian methods incorporate prior beliefs about model plausibility. Both frequentist and Bayesian approaches have roles in assessing evidence. Even with these methods, some limits remain fundamental. If a collision occurred in a region that lies mostly beyond our cosmic horizon, most of its signature never reached us. If the collision energy scale was low, the imprint it left may be below the sensitivity of any realistic instrument. If a collision happened so early that later processes erased its marks, no present test will find it. Null results are informative but limited. When searches find no evidence, scientists set upper limits on how common or how strong events can be. These limits rule out regions of parameter space in theoretical models. Over time, tighter limits narrow the viable models. Yet a null result does not prove an idea false in all its forms. It shows that either the events do not happen at the level that would be visible from our location, or that the events are rare, or that their effects are small. Progress requires persistence and many independent improvements. Better instruments with lower noise and wider frequency coverage reduce foreground uncertainty. Longer surveys increase the sample of galaxies and lower shot noise. More pulsars and longer timing campaigns improve sensitivity to very low frequency gravitational waves. Larger simulations cover more model space and provide more accurate templates. Better algorithms and more careful treatment of systematics reduce biases. Time is another limiting factor. Building a new satellite or a large ground-based facility takes many years. Collecting enough data can take many more years. Detecting a weak, rare signal may require decades of observation and analysis. Scientists plan long-term programs and make incremental improvements that together extend the reach of their tests. The search for signs of other bubbles combines many difficult elements. The universe limits what we can know. Instruments and the sky itself limit what signals we can extract. Theory and computation limit how fully we can explore predictions. Human factors limit how cleanly we can analyze data. Together, these limits explain why a discovery would be hard to reach and why claims must be tested by many independent methods. At the same time, the limits show the path forward. A careful program of multi-frequency observations, deep galaxy surveys, long gravitational wave monitoring, precise spectral measurements, and large-scale simulations can push the limits outward. Combining independent probes reduces the chance of false alarms. Requiring consistent evidence across different types of data raises the bar for a convincing detection. If a clear and robust signal ever appears, it will have to survive all of these challenges. It must be consistent across different observables. It must be unlikely to arise from noise, foregrounds, or instrument errors. It must fit a coherent physical picture that remains plausible under theoretical scrutiny. Meeting these criteria is hard. That is why the search proceeds with care, patience, and rigor. If scientists ever found a clear and robust signal that another bubble touched ours, the effect on science would be very large. The discovery would change how physicists describe the origin of space and the rules that govern particles and forces. It would also change how experiments are planned and how large projects are prioritized. This chapter explains the meaning of such a discovery and the practical path that would follow. The language is simple, the steps are clear. Immediate scientific consequences. A confirmed detection would show that our observable region is not the whole story. It would prove that different regions of space can have different basic rules. That fact would require new physical laws that describe how bubbles form and how their internal rules are set. Physicists would need equations that predict which states a field can take and how likely each state is. Theories of inflation and of the fields that drive it would gain new direct data. Measurements of a collision would give numbers. Those numbers would constrain the energy scale of the transition. They would constrain the thickness and speed of the bubble wall. They would constrain how much energy went into motion, into particles, and into radiation. Those constraints would narrow the possible shapes of the field potential that produced inflation. Particle physicists would use the new data to test ideas about high-energy physics. The internal rules of our bubble come from high-energy fields. A collision signal that points to certain field values would favor some particle physics models and disfavor others. For example, the data could tell whether additional light fields were present early on, whether extra spatial directions were relevant, or whether new particles were produced by the collision. These results would feed into the program of building a unified theory of particles and forces. Cosmology would also change. A clear detection of bubble interactions would demand a new statistical description of what kinds of bubbles exist and how common each type is. This distribution would let scientists ask whether our set of physical constants is typical among observers or rare. That shift would place the old question of fine-tuning on a different footing. Instead of treating constants as unique universal truths, scientists would study distributions of possible values and the conditions that allow observers to exist. Philosophy and worldview. The discovery would raise deep conceptual questions. People would ask what counts as physical reality beyond what can be observed. If many bubbles exist beyond our horizon, is their existence part of physical science? Scientists and philosophers would work together to define what is testable and what counts as physical explanation. Questions about the origin of the inflating phase and about whether the multiverse is finite or infinite would gain urgency. Researchers would ask what started the process that made bubbles. They would explore whether there are limits on the number of possible states. These are questions at the border of physics and philosophy. New data would push the boundary between them. New experiments and observations. A detection would motivate a broad experimental program. The goal would be to measure the signal in more detail and to search for other signatures predicted by the favored models. The effort would span many branches of observational science. Better full-sky maps of the ancient light would be a top priority. Satellites that measure the cosmic microwave background across many frequencies and with very low noise would be designed. These satellites would aim for much better polarization sensitivity and for many frequency channels to remove foreground emission. The design would include very stable detectors and tight control of systematics. Ground-based observatories would expand their sky coverage and improve depth in targeted areas. Balloon experiments would fill gaps between satellite and ground measurements. Gravitational wave observatories would be upgraded and extended. Ground interferometers would aim for greater sensitivity at higher frequencies. Space-based interferometers would be built to probe lower frequencies that ground instruments cannot reach. Pulsar timing arrays would add more precise pulsars and lengthen the timing baseline over many years. Together, these detectors would map a wide range of frequencies where a collision signal might appear. Large galaxy surveys would be expanded. A combination of wide and deep surveys would cover much of the sky and measure precise distances for many galaxies. Both spectroscopic and photometric programs would be planned to chart the three-dimensional distribution of matter and to improve weak lensing maps. 21-centimeter radio arrays would be built to probe the era when the first stars formed. Those arrays would map neutral hydrogen across a wide range of redshifts and would test for early heating or ionization from collisions. Spectral distortion missions would be developed. Instruments that measure the precise frequency shape of the ancient light would search for tiny deviations from a thermal spectrum. Those deviations reveal energy injection at different times. Detecting a mu-type distortion or a y-type distortion from an event would give timing information about when the energy entered the plasma. Laboratory experiments would respond too. If models predict relic fields or light particles, experiments in particle physics and in precision measurement would search for them. Atomic clock networks would increase in precision and in number. Magnetometers and resonant cavity experiments would probe weak couplings to new fields. Searches for missing energy or for new decay channels at particle colliders would be refocused to test the ranges suggested by cosmological data. The role of simulations and theory. To interpret any detection, theorists and simulators must work together. Numerical simulations of bubble formation and collisions would be improved. These simulations would include nonlinear field dynamics, the expansion of space, and the conversion of field energy into particles and radiation. They would follow the outcome through reheating and into the era when the ancient light formed. Simulations would also create synthetic observables. They would make mock maps of the cosmic microwave background, of galaxy distributions, of lensing maps, and of gravitational wave spectra for a wide range of parameters. These mock data would pass through realistic instrument models that include beam shapes, noise, and foregrounds. End-to-end simulations would allow analysts to test detection pipelines and to estimate the probability of false alarms. Theory work would focus on connecting high-energy models to low-energy observables. Physicists would derive how field values in different minima map to particle masses and coupling constants. They would compute the expected distribution of states in a given model and would predict the statistical properties of bubbles that form. This work would turn qualitative ideas into precise predictions that experiments can test. Open data and independent confirmation. Given the importance of a discovery, independent confirmation would be required. Multiple instruments would need to see consistent aspects of the signal. Independent teams would analyze the data with different methods. Data sharing and open code would help other groups reproduce results. Blind analyses would be used to prevent bias. A robust program would require the same signal to appear in more than one observable channel. For example, a disk-like feature in the cosmic microwave background that also shows a matching polarization pattern and that aligns with a local anomaly in galaxy counts and with a gravitational wave burst would give strong confirmation. Multiple independent observables reduce the chance that a false alarm or a systematic error produced the result. Mapping the diversity of bubbles. If some collisions are detected, the next step would be to map how common different bubble types are. Scientists would measure the rate of collisions, the distribution of their energies, and the variety of imprints they leave. Those measurements would constrain the underlying theory of inflation and fields. With enough detections, scientists could start to estimate how physical constants vary across bubbles. They could study the distribution of coupling strengths, particle masses, and vacuum energies. That information would let them test whether observers are likely to find themselves in a bubble with our specific parameters. The question of fine-tuning would become a statistical problem about typicality in a set of bubbles rather than a single unexplained fact. Practical timescales and costs. Major new satellites and large ground facilities take many years to build. Planning, design, funding, and construction can span 1 decade or more. Data collection can take another decade for long surveys. Gravitational wave detectors and pulsar timing arrays need long observing runs that extend over many years to reach the desired sensitivity. Numerical simulation campaigns require sustained computing resources over many years. Funding agencies and international collaborations would coordinate long-term programs. The required investments are large. Building space missions and large arrays needs significant funding from governments and institutions. Large collaborations would form that cross-national boundaries. The effort would be similar in scale to other big science projects that map the sky, probe fundamental physics, or study Earth and the planets. Philosophical and public engagement. The discovery of bubble interactions would attract broad public interest. Clear communication would be essential. Scientists would explain what is known and what remains uncertain. They would emphasize what the data show and what assumptions went into the interpretation. Open engagement with philosophers and the public would help frame the implications for our place in the larger reality. The discovery would also provoke questions about the limits of scientific knowledge. People would ask whether parts of reality beyond our horizon are meaningful in the same way as the region we can observe. These are deep questions that require careful thought. Scientists would work with philosophers and educators to explain what can be tested and what remains speculative. Limits on what a discovery would prove, even a strong detection, has limits. A single kind of signal might be explained by more than one physical model. Some signatures, while consistent with bubbles, could also be generated by exotic but internal processes. Therefore, a robust case would require multiple independent signals and a coherent theoretical explanation that matches all observables. A discovery would not answer every question. It would not automatically tell us what started the inflating phase. It would not alone prove whether the multiverse is finite or infinite. Those remain open problems that would require further theoretical and observational work. The long view, finding evidence that our bubble met other bubbles, would change the practice of physics. It would make cosmology and particle physics work in even closer partnership. It would require new kinds of experiments and new thinking about what counts as a physical law. It would open a new branch of empirical study that tests how laws can vary across space. At the same time, the discovery would show how science advances. It would come from careful measurement, from independent confirmation, and from a long program of theoretical and computational work. It would also rely on global cooperation and sustained support for large projects. A final note. The search for signs of other bubbles tests the limits of what we can observe. The work is difficult. The evidence must be strong. If such evidence appears and stands up to scrutiny, it will change how people think about the origin of the universe and about the nature of the laws that govern it. The path from a tentative signal to a confirmed discovery will be long and careful. The rewards for success are deep and far-reaching.